So what you do for your next step, even though it's still step one, the next step in step one is to downscale the temperature and precipitation effects of those two scenarios across the 6 GCMs that you're looking at. So you can see, you may not be able to read it, but there are lines in each of these charts for those 6 models, and then the heavy black line is the average of those 6 models going out to 2100. The first column is temperature, the second column is precipitation, the top row is scenario B1, and the bottom row is scenario A2. B1 was the more optimistic green line, A2 was the more pessimistic high line that I pointed out. So what you can see with temperature is that in the first 50-year chunk there, from 1950 to 2000, they're actually replicating historic, or at least they're consistent in their treatment of historic temperature. And then as you get into the projections going forward up to 2100, you see that the optimistic scenario gives you about a 2 degrees Celsius on average temperature increase, and A2 gives you about a 4 degrees Celsius increase on average projected across those. You also see that for precipitation, that heavy black line really doesn't show you a predominant trend. There's a lot of variability around the average, and so we end up not getting a lot that's very useful for a grid cell from these global circulation models. And again, it's because precipitation is more difficult to deal with. There are a lot more in the way of localized terrain issues that will affect your mountains and so forth that will affect precipitation. It's a lot more difficult for these models to project that. So we move on for precipitation to a weather generator. And there are lots of different kinds of weather generators, and there are lots of things that weather generators aren't particularly good at. But one thing that they are good at is looking at temporal change for a specific location for precipitation. And so that's what we've used here to supplement the temperature projections from the GCMs, is to look at essentially calibrating the weather generator to observe historic data at the area, at the basin, and then use that calibrated data perturbed by the temperature data from the GCMs to generate essentially replacement precipitation inputs for the location. So that's projecting climate change for us for the next 100 years. And up above this reminder again of the complexity of the systems, you see we have now the GCM simulated temperature that we're relying on, the weather generated precipitation, and another key thing here is that this is all daily now. As computing power gets better and faster and less expensive, what we can actually do now is move from monthly time steps to daily time steps, which is extremely important for hydropower plants when you're expecting changes in precipitation going forward. If your monthly average may not change a lot, but the actual rainfall events might become smaller and more acute within a month, and that's very important to know for all sorts of obvious reasons. So we take the outputs from those global, from the global model downscale to the local levels, and then we start to run it back through more traditional evaluations that are always done, that can be done for hydropower projects. So we look at the rainfall runoff that's available now in light of evapotranspiration and soil saturation, and so we see what's available to the coming into the river. We look at how it's channeled down the river, again using, in some cases, publicly available models from the Hydraulic Engineering Center of the U.S. Army Corps of Engineers. They have a hydrodynamic model that you can use if you have enough inputs to model it. And then we move on and take that water into the reservoir and look at the rules, the operational rules for the hydropower plant, and we can actually come up with what the actual generation is going to look like from that plant. Again, in the future, in light of this changing availability of precipitation, primarily coming into the system. We can do a financial analysis to see what that means for the viability of a new project, and ultimately, at the end of the day, we look at the fact that we have competing uses for a dwindling resource. And you know, you have direct impacts, indirect impacts. There's a lot of this that can't be modeled very well, that has to be done more heuristically or subjectively. And but it's rather than be gloom and doom about it as I finish up, I want to be rosy about it, because it's always better to be proactive and to understand the reality of what you have to deal with in advance. If you're dealing with it retroactively, your response options are usually a lot more limited. So that's my take. Thank you. Questions? That's drinking from a fire hose, I know.
I do have a question.
Yes, sir.
You give all these models and train and so forth. Actually, in this world, we already have the recorded flows, durations, seasons already available. Why don't we use the system available to make use of it, and rather than work on academic models?
We do use historical existing information. We use existing tools. That's what I meant at the beginning when I said it's not really changing the rules of the game, it's just changing the approach, the strategy, which is that we have to remember that climate change is in fact is making historic information a poorer predictor of the future reality that these hydropower plants and other infrastructure is going to have to deal with. So you take your existing tools, but you have to inform them with this new these new estimations of related to climate change.